Good morning guys and welcome back to Dynamics course. In this video lecture we're going to talk about erratic motion. So what is an erratic motion? Erratic motion means a weird motion that is unpredictable. It's usually represented graphically using a set of curves. These curves are used to describe a relationship between any two of the following variables: acceleration, velocity, position, and time. And these are the variables of kinematics. Now, how can I find the other variables? In fact, I can use the set of equations that we talked about in the previous video, like for example the equation of acceleration versus time, which is a is equal to dv over dt, the equation of velocity that is equal to ds over dt, and don't forget the independent equation of time, ads is equal to vdv. Using these equations, I can find out what are the other variables that are not represented in this graph. So guys, in many experiments, a velocity versus position profile is obtained, right? So here I don't have a velocity versus time. I have, for example, the velocity versus s. So what do you think, guys? From this graph, can I find what is the acceleration at a certain position? For example, can we determine the acceleration of this motorcycle represented in this graph at a position s is equal to 175 meters? In fact, yes, using one of these equations, which is the independent equation of time, ads is equal to vdv, I can find the acceleration. So guys, a graphical representation is a good way to handle especially complex motions like erratic motion that would be difficult to describe with formula. For example, guys, if I take the first graph here, I have a representation of s versus t. Alright, so this is a two-variable representation, the position versus time. From this plot, from the plot of position versus time, can I find the velocity versus time? Of course, guys, because I know that v is equal to ds over dt. So this is the instantaneous equation of velocity, or this is the instantaneous velocity. Alright, so if I know the slope, if I can find the slope graphically of any point on this graph, this will be the velocity. Alright, so in this case, guys, finding the slope of the line tangent to the motion curve at any point will be the velocity at this point, at this time. Therefore, guys, the velocity versus time graph can be, of course, constructed by finding the slope of which graph? Of s versus t. Now, if I know v versus t, can I find the acceleration? Guys, yes, of course, because I know also that this acceleration is equal to dv over dt. So this is the instantaneous equation of acceleration, which means, guys, if I know the graph of velocity versus t and I can find the slope of the line tangent to this velocity curve at any point, I can find the acceleration at this point or at this time. For example, here, if I can find the slope graphically, of course, I can find a2, right? So from s versus t, I can find the curve of velocity versus t and the curve of acceleration versus t. Now, what if I have the opposite? What if I have the acceleration versus t? So if I have the first place, the acceleration versus t, can I find the velocity and then can I find the position? Of course, guys, because in fact, I know that dv is equal to a dt, and I know that the integration of dv will be, of course, the integration of a dt plus a certain constant, or I can say it is the integration of dv between v1 and v2 is equal to the integration of a dt between t1 and t2. Now, how can I relate this equation to the graph here, which is the representation of A versus time? In fact, guys, if I know the curve of A versus time, this integration is nothing but the area under this curve between T1 and T2, right? So this is the area under the curve between T1 and T2. And this means, guys, that delta V is equal to delta V between 1 and 2 is equal to the area under the curve of A versus T between T1 and T2. But if I know delta V, how can I find V for each T? In fact, guys, if I know the initial velocity of the particle, so I know V0, then I can find V1, then I can find V2, I can find V3, and so on. Alright? So what should I do? In fact, delta V, which is V1 minus V0, will be equal to the area under A between T1 and T0. And since I know V0, so I can find V1 and so on. I can find all the velocity points versus the time T. In the same way, I can also find S, alright? So delta S will be what? Will be the area under V, under the curve of V versus T. So delta S is the area under V under the graph VT. So if I know also S0, I can find S1, because in fact S1 minus S0 is the area under VT between T1 and T0, and then I can find S2, and then I can find all other points, right? So if I know, guys, the graph of acceleration versus time, using the area under the graph, I can find all the points of velocity, all the points of position versus time. Now what if I have a more complex case where the acceleration, like this case, is given versus s? What should I do? In fact, guys, from this equation, the independent equation of time, v dv is equal to ads, I can use this equation in order to solve for velocity in this case. Alright, so what is v dv? If I do the integration, guys, then I am gonna find this equation between t1 or between v1 and v0, right? So if I do the integration between point 0 and 1, so this will be half v1 squared minus v0 squared is equal to what? It's equal to the integration of a ds between s0 and s1. And I know, guys, that this is the graph of a versus s. The integration of a ds is nothing but the area under this graph, right? So if I know v0, I can find v1, right? Because I know the area under the graph between s0 and s1, so I can find v1. And of course, guys, if I know v versus s, I can also find the acceleration, alright? So using the same equation, this acceleration will be v times dv over ds, alright? So what is dv over ds? It is the slope of the tangent line at this point times this velocity itself. So if I do the multiplication of this velocity at this point times the slope of the tangent line, I can find a at this point s. Alright, guys? So that's it for erratic motion. Of course, we're going to solve some problems on this type of motion later on. Thank you.